Welcome everyone to our course. Today we will learn about quantum dot based solar cell. In earlier few lectures, we introduced you the concept of first generation and second generation solar cell. In first generation solar cell, we have discussed about single crystal silicon solar cell, and what we learned that starting from the sand we can make a single crystal silicon, and this single crystal silicon is further doped to make a p-n junction silicon solar cell. Now, many times due to the use of the excess heat and the low yield, this process is very expensive. In the second generation solar cell or amorphous thin film based solar cell, we get efficiency which is less than the first generation solar cell, but the manufacturing cost is much lower in comparison to the single crystal silicon solar cell. That is why the most of the solar panels or solar modules that have been fabricated by this thin film amorphous silicon solar cell. Now, we introduced you the concept of the third generation solar cell also, and we discussed that due to the discovery of different materials, there are different varieties of third generation solar cell can be possible. Like if we use new kind of dye or sensitizer molecule, then we can fabricate dye sensitized solar cell. In one of our class, we have explained the photophysics behind this dye sensitized solar cell, and we have also demonstrated you how to fabricate this DSSC device in the lab. The fabrication of DSSC device that depends upon the choice of the dye and the electrolyte molecule. Similarly, using the organic polymer, we can make organic photovoltaics or organic bulk heterojunction solar cell. If we change the material from organic polymer to perovskite material, we can fabricate perovskite solar cell. Now, in this context, another important category of this third generation solar cell is quantum dot based solar cell. Now, today first we will discuss about what is quantum dot, how the quantum dot are made, and then how we assemble this quantum dot to fabricate a quantum dot based solar cell. So, before going to the quantum dot, first let us see, like which we have also discussed earlier, about the density of state. If you remember, the density of state is defined as the number of available energy states per unit energy per unit volume. It tells you how many states are available for the charge carriers for occupancy. We also have learnt that there is a probability distribution function which tells that at a particular energy E, what is the probability of occupancy of an energy state by an electron. And we have also seen that if we multiply the density of states with the probability density, which we defined as a Fermi distribution function, and if we integrate it over all possible energy state, then we get the total number of electrons or total number of holes in the corresponding band. Now, in the context of the density of state, we have seen that when we change the dimension of the material, the density of states change significantly. For example, if you look here, this 3D bulk material, here the electrons are free to move in all directions, and we have seen that the density of states in that particular case was proportional to e to the power half. And if we plot density of states versus the energy, then it looks like this graph. On the other hand, if you look a two dimensional bulk material, for example, a two dimensional graphene sheet, here the motion of electron is restricted from one dimension. So, instead of three different dimension, now electron are free to move in two direction. So, in the two dimensional system, the density of states is constant. We can write it as e to the power 0, because e to the power 0 is constant. And if we plot the density of states versus energy, for example, in a case of quantum well, it looks like the step function. The third system in this category is one dimensional bulk system. So, basically starting from a 3D bulk material, we are reducing the dimension one by one. You can take an example of a chalk, and let us reduce the dimension of the chalk by reducing one dimension at a time, and let us calculate what is the density of states corresponding to that particular dimension. Now, in one dimensional bulk material, motion of electron is restricted from two direction. So, that means electron are now free to move in only one dimension. In that case, the density of state is proportional to e to the power minus half or 1 over square root of E. And if we plot the density of states versus energy for an one dimensional quantum wire, it looks like this graph. Finally, we have a 0 dimensional material where the motion of electron is restricted in all directions, for example quantum dot. Now, in here the density of states is a delta function and which can take different values. As you have plotted here, the density of states is looks like a delta function. Now, this delta function kind of density of states that defines that at a particular position the value of the potential is infinitely high and at any other positions it does not exist. In the case of quantum dot, which are very small size particle, usually in a dimension between 1 to 10 nanometer size, the effect of quantum confinement happens, and because of that this kind of material shows a size dependent optical, electrical and mechanical properties, which usually we do not observe in a bulk material. That is an important features or characteristics of this quantum dot, and these quantum dots has been used to fabricate different kinds of optoelectronic devices like light emitting diodes or solar cell, that we will see. Now, if we compare some of the important parameters or properties of the bulk material to the nano material, so we can see that in some case we get certain advantage over using a nano material over a bulk material. For example, in this table you can look here. So, we are comparing, the first property we are comparing is the structure. Now, in the structure the specific properties is the confinement or surface to volume ratio. Surface to volume ratio is also called aspect ratio. Now, in the bulk state there is no confinement. So, electron is free to move in all three different directions, but in nano state like quantum dot, here it is confined in 0 or 1 or 2 dimension, and sometimes it is 3 dimension. So, basically we can also make a nanoparticle where all the 3 dimension exist, but the size is more than 10 nanometer. So, anything like let us say we make a nanoparticle of 100 nanometers. So, then we can't say that it is the motion of the electron in this nanoparticle is only confined in 0 dimension or 1 dimension. In this particular case the electron motion is confined or it is allowed in all 3 different directions. So, the confinement have a freedom in the case of the nanostate. Aspect ratio in the bulk material is small, whereas in the nano it almost approach to 1, where all atoms are the surface atoms. Now, if the aspect ratio is very high, so that means the probability of contact of any external molecules to this kind of systems is much higher. That is why the nanostate materials are very effective and useful for fabricating different kind of sensor material. Next important parameter is in terms of the electronic properties. Now, whenever we talk about electronic properties, the first thing come in the mind is the band gap. Now, we have learned that the band gap is the forbidden energy gap between the valence band and conduction band. In the case of the bulk material, the band gap value is constant, whereas in the case of the nano material the band gap is size dependent. So, what does it mean? Let us say I have a bulk zinc oxide, so or bulk titanium dioxide, the band gap value is 3.2 electron volt, whereas if I make a titanium dioxide of 100 nanometer and if I make a titanium dioxide of 10 nanometer, there will be a significant change in its band gap. Similarly, this quantum dot, if I have a quantum dot of 2 nanometer or if I have a quantum dot of 4 nanometers, their band gap value is different. So, we can have a tunable band gap in the same material system. Of course, the experimental condition of fabricating this material has to be different. Now, if the band gap is different, obviously its optical properties will also be different and some of its electrical properties will also be different. Thermodynamic properties like melting point, metals have high melting points, but metal nanoparticles have low melting points. So, in terms of melting points we do not gain much when you go from the bulk state to the nano state. Now, there are some other properties also we can compare, for example magnetic effect. Now, bulk ferromagnetic material, they usually form multiple magnetic domains, whereas a nanomagnetic particle, they consist of only one domain and exist a superparamagnetism. Density of states for a bulk material is proportional to always e to the power half or square root of E, whereas in the case of the nanomaterial we can get either a 2-dimensional structure or a 1-dimensional structure or a 0-dimensional structure. So, density of states for a 2-dimensional material is constant, for a 1-dimensional material it is inversely proportional to the square root of E, and for a 0-dimensional material it is different for individual energy levels, and we have seen that it follows a profile of the delta function. Now, since the density of states is different according to the different dimensions, now if we multiply with the Fermi-Dirac distribution function to get the number of electrons or holes in this system, so it will be different from 2d to 1d to 0d from the same material system. For example, let us say I have a carbon allotrope of a 3-dimensional material, a carbon allotrope of a 2-dimensional material, and a carbon allotrope of 1-dimensional material and a carbon allotrope of 0-dimensional material like carbon quantum dot. So, in all of these cases the density of states will be different, because although the material is made of carbon, the dimension of the material is different. Starting from 3D it goes all the way to 2D to 1D to 0D. Now, if the dimension is different, the density of states is also different. Now, if the density of states is different, when we multiply even the same value of the Fermi-Dirac distribution function, we will get the different charge carrier concentration. So, that is why we can see a significantly different value of the charge carrier dynamics and charge carrier concentration when we go from a 3-dimensional graphite to a 0-dimensional carbon quantum dot, and because of that their optical properties as well as electrical properties is way different. Now, the quantum dots actually was discovered a long back. History of quantum dot begins with their first discovery in glass crystal in 1980 by a Russian scientist Ekimov, and who have done a very systematic advancement on the research of the quantum dot, and it also led to the 1984 discovery by Louis Brass, who derived a relation between the size and band gap for semiconductor nanoparticles by applying a particle in a sphere model approximation to the wave function for bulk semiconductor. We can always find out a relation between the size of the nanoparticle and the band gap for semiconductor. For example, let us say the quantum dot CDAC, which is made out of cadmium and selenium, and if we know its band gap Eg and if we know its dimension, let us say d, so basically one can find out from the dimension what it will be the corresponding value for the band gap, or other way around, if I know the band gap we can find out the dimension of the particle. So, we have a tunability over the band gap, that means we have a tunability over the optical properties. It finally catches up the speed by successful synthesis of colloidal cadmium X. So, colloidal cadmium based compounds like cadmium sulphide, cadmium selenide or cadmium telluride with a core shell structures shows a size tunable band edge absorptions and emissions, and because of that this kind of quantum dots has become very popular over a very short amount of time, and these quantum dots can be made by solution based approach. CDX is the most investigated quantum dot due to their excellent optical and electrochemical properties. In most of our experiment we still use cadmium based quantum dot. It can be either cadmium sulphide, so we can write it as cadmium sulphide, or we can write it as cadmium selenide, or we can write this as cadmium telluride. So, any of these combinations we can make it by suitably choosing the precursor materials and the reaction condition, and by changing the temperature of the growth we can also control the particle size for each of these quantum dots. So, what is the definition of quantum dot then? Quantum dots, which is also abbreviated as QD, they are the tiny semiconducting particle, usually a few nanometer in size, as I said usually less than 10 nanometer, having optical and electrical properties or electronic properties that is significantly different from the larger corresponding bulk particle. Many types of quantum dot, when excited by electricity or light, emit light at frequency that can be precisely tuned by changing the dot size, shape and material. So, what does it means is that let us say even if I have this material cadmium selenide, So, by changing its size or by changing its shape, we can change its emission or photo emission properties. So, that means we can make a light emitting diode as per our desired emission wavelength just by changing the size or shape of the cadmium selenide. Similarly, if we go from cadmium selenide to cadmium telluride or cadmium telluride to cadmium sulphide, we can also change or tune its optical properties. So, that is one of the biggest advancement the quantum dots provide us, the tunable optical and electrical properties based on the size, shape and material. Quantum dots are sometimes referred to as artificial atoms, emphasizing their singularity, having bound discrete electronic states like naturally occurring atoms or molecules. Now, we know that in atoms or molecules we have discrete energy states. Now, in quantum dots the energy states are also discrete. So, that is why sometimes they are also called artificial atoms. Quantum dots have properties which are intermediate between bulk semiconductor and discrete atoms or molecules. Now, if I have a single atom or molecule of a zinc oxide and if I have a bulk zinc oxide, there is a huge difference in their properties. Now, quantum dot has properties which is not similar in either one of them. Their optoelectronic properties changes as a function of both size and shape. Larger quantum dots of 5 to 6 nanometer diameter, they emit longer wavelengths with color such as orange or red. Smaller quantum dot like 2 to 3 nanometer, they emit shorter wavelengths yielding colors like blue and green, although the specific color and size they are very much depends on the exact compositions of the quantum dot. Now, although this is a trend, but we cannot generalize this statement. Usually what we see that these quantum dots with 5 to 6 nanometer size, they emit something like orange or red color, but the quantum dots which are like 2 to 3 nanometer, they emit blue color. But this is not a very general statement, it also depends upon what particular kind of quantum dot we are taking or what particular kind of quantum dot we are using for making our device. Because of their highly tunable properties, quantum dots are of wide interest. Potential application, they are used very extensively in fabricating transistors, solar cells, light emitting diodes, diode lasers and also second harmonic generation. Second harmonic generation is a nonlinear optical effect. So, here starting from one particular frequency we can generate different kind of frequency. Different kind of frequency means different kind of color. Quantum computing, an area which has become very popular nowadays, and medical imaging. So, since this quantum dot has a very strong degree of fluorescence emissions which is often quantified it by its quantum efficiency of fluorescence, and quantum efficiency of fluorescence for quantum dot is quite high. So, that is the reason these guys are very potentially good candidate as a fluorescence probe or imaging probe in medical imaging. So, not only in optoelectronics devices like solar cell, LED or transistors or lasers, they are also used in sophisticated applications like quantum computing and also in medical imaging. Now, coming to the synthesis of the quantum dots, there are three main methods we follow to make the quantum dot. The first method is a more physical based techniques called lithography. The second method is a solution based approach called colloidal synthesis. This is relatively easier to make in the lab. And then the third method is also another physical techniques called epitaxy, pattern growth and followed by the self organizations of this nanoparticle. Okay. So, let us come to the first procedure called lithography. The word lithography that comes from the Greek word lithos meaning stones and graphia means to write. So, if you see that this word lithography, they contains two different syllabi or they contains two different parts. One is litho which comes from the Greek word lithos, and lithos means stones, and graphy it comes from the Greek word graphia which means to write. So, if we convert it a verbatim translation from the English to the Greek, so the meaning of lithography is literally writing on stones. So, by the process of lithography we usually mean patterning, and patterning any particular kind of semiconductor substrate. So, lithography or patterning refers to the series of steps that establish the shapes, dimensions and locations of the various components of the integrated circuits. For lithography processing, a hard copy of pattern has to be first generated. This is called a reticle or a mask. So, for doing the lithography, which can be electron lithography or photolithography, So, where in electron lithography we use an electron beam to write the pattern, in photolithography we use an optical beam to write the pattern. But in either case, to write the pattern we have to have some kind of structure or some kind of mold using which we can generate the patterns, and that mold or structure is called mask or reticle. Lithography can be divided into photolithography. In photolithography we use light source or optical beam like laser light to write the structure. Electron beam lithography or E-beam lithography, where we use electron beam to write the structure. This sometimes comes with the scanning electron microscope or SEM. Then X-ray lithography, where we are using X-ray beam to make the structure, and ion beam lithography. Here we use the highly energetic ion beams to make the structure. Now, for the fabrication of quantum dots, we usually use electron beam or ion lithography. Okay. So, in electron beam lithography, like that is an ion beam lithography, both are quite complicated process, but we will try to see in a more simplistic fashion. For example, quantum wells. So, we start with the quantum wells and they are covered with a polymer mask. Just like here, you see this is a quantum well which is a two dimensional structure, and this quantum well has been covered with a polymer mask as shown in the beam here, and an electron beam is falling from the top. So, quantum wells are covered with a polymer mask and exposed to an electron or ion beam. So, in this picture here there is a quantum well which have been covered with a polymer mask, and on the top there is an electron beam is coming. Instead of electron beam, one can also use ion beam. The surface is covered with a thin layer of metal, then cleaned, and only the exposed area keep the metal layers. Now, the next step is the B. You see there is only a thin layer of the metal which is only exposed, which we wanted to develop. Pillars are etched into the entire surface. Multiple layers are applied this way to build up the properties and size wanted. And there are some disadvantages associated with this process. This method is slow. This always involves some contamination, and the density of the material is low, and sometimes we also generate defects or trap states while fabricating by this method. The another important technique is the epitaxy or pattern growth. Semiconducting compounds with a smaller band gap, for example gallium arsenide, are grown on the surface of a compound with a larger band gap like aluminum gallium arsenide. Now, growth is restricted by coating it with a masking compound. As a masking compound, we usually use silicon dioxide and etching that mask with the shape of the required crystal cell wall shape. The main disadvantage of this method is the density of the quantum dots limited by the mask patterns. So, whatever the mask pattern we will generate, that determines how many quantum dots we will be able to make in this process. For example, in this figure we are showing that, like you can see that on an indium gallium arsenide substrate, we have put in a gallium arsenide substrate and then we are etching it in the presence of the silicon dioxide. Using a large difference in the lattice constant of the substrate, here in indium gallium arsenide, and the crystallizing materials helps the epitaxial growth. When the crystallization or the crystallized layer is thicker than the critical thickness, there is a strong strain on the layers. The breakdown results in randomly distributed isolates of regular shape and size. Some of the disadvantages associated with this method are size and shape fluctuations and the ordering of the material. Now, the third method, which is popularly used in many of the research labs as well as in some of the industry process, is the colloidal synthesis of quantum dots. One of the advantages of colloidal synthesis is that, in apart from the fact you can make it in a bulk amount, you can also make it on a flexible substrate, because you can print it or you can blade coat it on a flexible substrate in a roll to roll basis. The quantum dot synthesis methodologies have progressed substantially in the past 2 decades, and various synthetic approaches have been developed for the synthesis of quantum dots, ranging from liquid phase methods to vapor phase epitaxial growth. The liquid phase methods have the potential to produce highly dispersed quantum dot in a various solutions with less energy demanding process. A traditional approach for the synthesis of quantum dots relies on the heating of specific organic solvent and injection of semiconducting precursors, as the schematic diagram shown in the next figure. So, as you can see here, like here we are showing a hot plate. So, this is a hot plate, and there are 2 knobs in this hot plate. One is for the rotation and another is for changing the temperature. Now, we have put a conical flux which has 3 neck. You see here, this is one neck, this is the second neck, and this is the third neck. So, a 3-necked conical flask has been put on a beaker which has been kept on a hot plate or a heater. Now, what happens, like we purge from one of the neck or one of the inlets the nitrogen gas, and the precursor molecule is purged from this inlet, and we also substantially heat the material. So, whenever, like for example, let us say I have to make CdAc or cadmium selenide. So, I have to choose a precursor for cadmium and I have to choose a precursor for selenium, and these precursor materials are injected from one of these inlets, and then nitrogen is bubbles, and we precisely control the temperature by using this hot plate, and then within a certain interval we take out the dispersants and cool it down, and depending upon the time interval you allow the reaction to proceed, you can have a different size distributions in the quantum dot. For example, here, like we are showing a particular size distribution for the quantum dot. The absorptions and fluorescence has been plotted in a same graph as a function of the wavelength. The first graph, this is showing the absorption spectrum, and as you can see that this absorption is somewhat like around like 425 to 430 nanometer range, and which has also a tail which has an end here also, like somewhat around 550 nanometer. And when you excite this quantum dot at its absorption maxima at 420 nanometers, so it emits with a color which is equal to somewhat around 550 nanometers or yellow color. Now, in the ACM image, an high resolution ACM image has been picked up this quantum dot. As you can see from this figure, the scale here is 20 nanometers, and if you look that if this much is the 20 nanometer and this quantum dot we are showing just by one dot. So, the particle size is hardly about 2 to 3 nanometers, and again like this particle size can be always be tuned depending upon the experimental condition of the synthesis. At what time we take out the particle, or how much heat we are providing, or how much precursors we are providing, based on that we can even change the size and sometimes the shape of this quantum dot. In a typical preparation method of cadmium selenide quantum dot, for example, the cadmium precursor and the selenium precursor solutions are first prepared by mixing cadmium CH3 and elemental selenium in liquid trinitro-octyl phosphine or top solutions respectively. So, the precursors are here. For cadmium it is CdCH3 and for selenium it is elemental selenium, and we take these two precursor in the presence of the TOP solutions, which are then rapidly injected into the heated trioctyl phosphine oxide or topo solutions under an inert atmosphere, and the inert atmosphere is maintained by purging the nitrogens. In a batch reactor, typically a 3-necked round bottom flask. So, in the previous diagram we have shown that. So, in there we are injecting through one neck this cadmium CH3 and the other neck elemental selenium in the presence of the top, and the beaker already contains the topo solutions. We are providing the heat and also maintaining the inert atmosphere. Here topo serves as the stabilizing agent and high boiling solvent, which allows the mixture to reach high reaction temperatures up to 320 degrees centigrade. A series of quantum dots with different size from 1.5 to 11.5 nanometer could be obtained over a period of few hours by controlling the growth temperature. So, as we said that by changing the temperature and by changing the time, we can control the size of these CdAc nanoparticles. Now, what are the potential applications for this quantum dot for solar cell? Like for example, photovoltaic devices like solar cells. In biology, this has been extensively used for fabricating biosensors and bioimagings, for making light emitting diodes like LEDs, quantum computations, flat panel displays, memory elements, photodetectors and lasers. These are some of the potential applications where quantum dots has been used very extensively. But our the syllabus that includes the quantum dot for fabricating solar cells. So, we will discuss in details how quantum dot can be used to make solar cell. Quantum dots have attracted considerable attention for photovoltaic application due to their perfect crystallinity and unique optoelectronic properties, which are defined by the particle size, shape and also controlled by the growth process. Quantum dot with their characteristics of sharp absorption onset are excellent candidates as absorber materials in third generation photovoltaic solar cells such as quantum dot sensitized dye sensitized solar cells. Well, whenever we talked about dye sensitized solar cells, we have said that when we choose a dye molecule or when we choose a sensitizer molecule, the first thing we consider how good it is absorption, or where does this material absorb, whether the material is good enough to absorb in the visible range and how much is its absorption coefficient. Now quantum dot does this job very well. It has a good absorption onset and its absorption coefficient is also quite high as comparable to other dyes. So that is why quantum dot is used to make a quantum dot sensitized DSSC device. In contrast to the large number of atoms in bulk material, the quantum dot consists typically of only 100 to 1000 atoms. So usually 100 to 1000 atoms are there in a quantum dot. The energetic structure of quantum dots changes dramatically with respect to bulk because of quantum confinement effect. Now the quantum confinement effect, that is a very important effect which happens only in quantum dot, and because of that this shows a size dependent optical properties. In bulk, the photogenerated carriers can move freely throughout the material, whereas in quantum dot the photogenerated charge carrier are confined in the 3 special directions of the quantum volume. Quantum dot solar cell have the potential to increase the maximum attainable thermodynamic conversion efficiency of solar photon conversion up to about 66% by utilizing hot photogenerated carriers to produce high photovoltage or high photocurrents. Now in a single crystal silicon solar cell or in a single crystal solar cell, there is a thermodynamic limit called quasi-Shoklar limit, and according to quasi-Shoklar limit there is a particular limit of the efficiency we can get from a single junction solar cell. But when we use a quantum dot, so by using a thermodynamic conversion efficiency of the solar cell that can even beat the quasi-Shoklar limit, it can reach up to 66%. How it does it? By using hot photogenerated carriers to produce higher photovoltage or photocurrent. The two fundamental pathways for enhancing the conversion efficiency or increased photovoltage or increased photocurrent can be accessed in principle in 3 different quantum dot solar cell configurations. These configurations are shown in the next figure. As you can see here, like where we are showing the 3 different configurations of the quantum dot solar cell. A quantum dot array used as a photoelectrode for a photoelectrochemical or as the I region of the PIN photovoltaic cells. So here this quantum dot is used as an I region, so the intrinsic regions of a PIN junction device or PIN solar cells. You see here on the left side I have a TCO electrode. This is a transparent conductive oxide electrode. For example, like an ITO, indium doped tin oxide glass substrate, or FTO, fluorine doped tin oxide glass substrate. Any of them we can use as a TCO electrode. On top of it we have put a semiconductor titanium dioxide, okay, and the titanium dioxides now absorb this quantum dot. And what quantum dot we are using here? Indium phosphide. Indium phosphide or INP is a quantum dot, and we are using a dimension of 30 to 50 angstrom. Now this quantum dot, like they will go and sit inside the mesopores of the titanium dioxides. Now what will happen? Now when the light falls on it, so the electrons will go from the ground state of the quantum dot to the different excited state of the higher excited state of this indium phosphide quantum dots. Now it has a band gap of 1.4 to 2.4 electron volt. What will happen, like the electrons in the excited state, now it will be injected to the conduction band of the titanium dioxides, and using the conduction band, then again it will go from here to the tissue and it will come to the outside circuit. Now there is a hole in this process which is generated, which is in the valence band now. Now to regenerate this hole, we use the iodine triiodide electrolyte, a very similar recipe which we used in a DSSC device. Now the catch is here, like here because of the quantum confinement effect, we have a discrete energy band gaps, a tunable energy band gaps in the excited states. So the excited electron can access any of the energy levels. So because of that, the possibility of the electron excitement from the ground state is multifold or manifold. So we have more number of electron excitation possible in this kind of solar cell. For example, here for Eg or the band gap for a polymer is showing here, EV of the H plus conducting polymers, it is showing in the right hand side. Quantum dot used to sensitize a nanocrystalline film of a wide band gap oxide semiconductor like titanium dioxide for absorbing the visible light. This configuration is analogous to the dye sensitized solar cell, where we have replaced the dye with the quantum dot molecule. Now as we have just explained that in a quantum dot in a SC polymer blend, like in a semiconducting polymer or in a conjugated polymer, let us say I take a conducting polymer like polythiophene and I put some quantum dot in there. So what will happen, like this is a whole conducting polymer and this is another electron conducting polymer. So now when the light falls on this quantum dot, for example indium phosphide, they absorbs the light and the electron goes from the valence band to the conduction band, right, and so there is an electron in the excited state and there is a hole in the valence band. Now usually for a charge conduction, electron participate in the charge conduction. Now you see that there are different discrete states due to the quantum confinement effect in the excited state of the quantum dot. Now electron can jump in any of these excited state. From these states electron can jump to the nearest electron conducting polymers. since the energy level matches with this electron conducting polymers. But in its neighbor there is also a hole conducting polymer. Now this hole conducting polymer will be able to grab the hole from the valence band or from the lower energy states of this quantum dot. So in this process we are utilizing both electron and hole. So whenever we are using a conducting polymer or a semiconducting polymer which is a hole conducting polymer and an electron conducting polymer in conjunctions with a quantum dot, so the possibility of extracting electrons and holes are equal. Even if it is not equal, so at the same time we can extract the electron, we can also extract the hole to some degree. So that contribute to the increase of the photocurrent. For example, like this is a bulk material and you see that this is the valence band and this is the conduction band, and sunlight is falling on both of this material, where on my right hand side there is a quantum dot, and in the quantum dot instead of valence band and conduction band we call it as a HOMO energy level and LUMO energy level. Now we have learnt that HOMO stands for highest occupied molecular orbital, whereas the word LUMO that stands for lowest unoccupied molecular orbitals. So here in organic polymers or in quantum dots, the organic polymers are in quantum dots, the orbitals are defined in terms of molecular orbitals. Now this is the highest occupied molecular orbitals, so that is actually valence band at 0 Kelvin temperature, and this is the lowest unoccupied molecular orbital, that is actually the conduction band at 0 Kelvin temperature. That is why these two energy levels are called HOMO and LUMO energy level. Now we have two different systems. Let us say on the left hand side there is an indium phosphide bulk material, on the right hand side we have an indium phosphide quantum dot, and here the light is falling on both the material. So the electrons, it will be going from the valence band to the conduction band. Here also there is the electron is there, when photon falls on that, so electron goes from the valence band to conduction band. What you see, they have separated the charge carrier. So electron is here and holes is in the valence band, and these electrons they emits as a heat. Whereas in the second case the same light is falling on the quantum dot. Let us have a look on this figure. Now I have two electron in my ground state, photon beams falls on the electron, one electron jumps from the valence band to the excited state or HOMO to LUMO level, leaving a hole in the HOMO energy level here and one electron here. What happens to the next charge carrier? Before that the electron comes to the lowest unoccupied state and there will be a photon emission. And now the second electron that goes from the ground state to the excited state or HOMO to LUMO level, leaving a hole behind. So here in the bulk case we have one exciton, here we have two excitons. So by similar approach here we get only one exciton, but on the right hand side we get two excitons. So if I have 10,000 quantum dots, so I gain 10,000 into 2. So I get 20,000 excitons in comparison to the 10,000 excitons in a bulk case. So that is the advantage of using quantum dot as a sensitizer. So this was about our quantum dot based solar cells, and as we have mentioned that here you can increase the efficiency of this device significantly, and even sometimes we can cross the thermodynamic limit by using two different kinds of polymers. And quantum dot based solar cells are relatively easy to fabricate. We can make it either by a physical methods like epitaxial growth or by photolithography or electron beam lithography, or the most popularly by solution based or colloidal approach, where we take the precursor molecules in a 3 neck conical flux, which we put it on a beaker, and also the beaker is placed finally on a hot plate. When we heat it and we add the precursor molecule in the presence of some kind of surfactant or some kind of stabilizing agents, and we allow the growth of the quantum dot. Depending upon the temperature and the time interval, the size and shape of the quantum dot is different. Now if the size and shape is different, their optical properties and electrical properties is also different. Now we can use this quantum dot either as a sensitizers or dye molecule in a dye sensitized solar cell, or also we can use them along with some conducting polymer, either with a hole conducting polymer or an electron conducting polymer. And we have observed that in comparison to the bulk material, the nanomaterials or the quantum dots they have an advantage of generating more kind of excitons or more hot charge carriers, which can contribute to the larger photocurrents and larger photovoltage in this kind of device. And that is why quantum dot based solar cells become very popular nowadays. Now for more reading and for a better idea, you can also refer to some of the excellent textbook like Quantum Dot Solar Cell by Professor A. J. Nozick, and Colloidal Synthesis of the Semiconductor Quantum Dots Towards Large Scale Production, a review paper by Feng Chen's group, and there are a lot of excellent research papers and review papers are also available in this area. So, you can also look for some of this to learn more about the quantum dot. Thank you very much.